Okay, in this video, I would like to discuss certain topics. This is in preparation for my Chemistry for Engineers long quiz, which is due in a few days. This is part 1, essentially. Might be 4 parts or 2 parts, depends, but this is basically part 1. So let's start. So what formulas are we going to use? We have the electromagnetic spectrum. That's we're gonna revolve our formulas on that topic. So essentially, frequency is equal to the speed of light, abbreviated as c, and it is divided by the wavelength, or abbreviated as lambda. And the unit is in nanometers usually. And since the speed of light is in meters per second, if you want to convert, then these are the ones that you have to know. So 1 meter, as you can see here, it is equal to 1 times 10 raised to 9 nanometers. Why is it raised to 9 specifically? So coming from meters, you move to decimeter, that's 1, and then 2, 3, 4, 5, 6, 7, 8, 9. That's where you get the exponent 9. Either this, you draw this, or if you want to be faster, you just simply memorize. So if you're converting, let's say, you're in a situation where you want to cancel the nanometer unit, you can use this. So 1 nanometer is equivalent to 1 times 10 raised to, this time it's negative 9 meters. So that's it for that part. So this is an example. If you want to convert a wavelength of 750 nanometers into meters, this, by the way, is technically still within the visible range. If you recall your Roy GBIV, so it's basically somewhere here between red and infrared. More on this later, once we get to the electromagnetic spectrum, which I already illustrated. So you multiply the value times with 1 meter over 1 times 10 raised to 9 nanometers. That way, you can cancel the units, the nanometer unit, and essentially in the calculator, you just divide 750 by 1 times 10 raised to 9, which you get this answer. So another thing you'd want to know is something called the angstrom. It's essentially a letter A with a circle on top. So this is the wavelength range of X-rays. More on this later, this is just one value. It helps if you are familiar with the corresponding values of all the members of the electromagnetic spectrum, to which X-ray is one of them. So yeah, wavelength range of X-rays and diameters of individual atoms. So again, oh yeah, I'll talk about it later completely. Let's go to, okay, we'll be skipping this part, more on that later. Let's go first to here, the electromagnetic spectrum. So this is pretty outdated. Let me just show you this part. It's easier to memorize using this illustration. It basically shows the same kind of idea. So where do we start? Here first. So gamma ray is usually 10 raised to negative 12. Always remember. And then again, like I said earlier, the angstrom, this is for X-ray, 10 raised to negative 10 is the value. For UV or ultraviolet, that's 10 raised to negative 8. For visible light, that's 10 raised to negative 6. So as you can see here, there's also extra information. This is Roy GBIV, but inverted, because the highest frequency is in the left side, and the lowest, consequently, is in the right side, to which radio wave has the lowest frequency, and at the same time, the longest wavelength. Okay, so after visible light, we have infrared. This is 10 raised to negative 4. By the way, the one I said earlier, the example is said to be 750 nanometers in wavelength. Like I said, it's between visible light and infrared. So, yeah. Microwave is 10 raised to negative 2. And between microwave and radio wave, it's just 1. And then by the time you reach radio wave, it's 10 raised to 2. Okay, so what is the sun's radiation composition that reaches Earth? So ultraviolet, that's 8%. Infrared, that's the most, with 53%. Visible light, that's 39%. Helps to know that. Okay, what's this question? A wavelength of a lamp was found at 570 nanometers. Calculate the frequency. So what was the formula that I used here? That's, well, the frequency abbreviation earlier is V. V or F, either way, as long as the formula is the same, the only difference is the letter that represents that value. So whether F or V, just use whatever you're comfortable with. Or unless your professor or teacher has instructed you to use a particular letter for that specific value. So this is the formula. Frequency is equal to the speed of light over the wavelength. So we all know the constant speed of light, whether it's not, even if it's not given in the question, it is implied. You should already know that the speed of light is always 3 times 10 raised to 3 times 10 raised to 8 meters per second. So 570, this is supposed to be nanometers. So you're gonna have to convert this into meters. And how would you do that? It's not seen in this computation, but let me show you. Usually if you want to be faster, you don't have to do this, but just to make sure that your answer is correct, you do this. So 1 meter is to what? 1 times 10 raised to 9 Newton meters. So after placing these values in the calculator, you would get, let me whip out my calculator in a while. For a while. Okay. So it appears to be that this one might be wrong. Good thing I was able to catch it now. Yeah. My mistake earlier was I perceived this to be in millimeters. It was supposed to be in nanometers. So this is not correct. Correction, 570 over 1 times 10 raised to 9, that is 5.7 times 10 raised to negative 7 meters. And using this as our new wavelength value, let's use the formula. F is equal to C over V. Speed of light is 3 times 10 raised to 8 meters per second divided by, or if you want to reciprocate already to remove the division, it's going to look like this. So 5.7 times 10 raised to negative 7 meters. Meters per second, you can write it like that, yeah. And so 3 times 10 raised to 8 divided by 5.7 times 10 raised to negative 7 is equal to 5.26 times 10 raised to 14. You can say over seconds, that's the unit, one of the units of frequency, or you can simply say hertz. And this is the final answer. So kindly disregard this part. It is not correct. Okay. Let me just confirm if my answer is correct. It's not that I'm not sure about my answer, but just to make sure that once this is uploaded on YouTube, I am not disseminating wrong information. As much as possible, I'd want to avoid it. Okay, it's confirmed this is the correct answer. Okay, what's next? Let's go to energy of radiation. It might not be the same thing with... Okay, before I end this video, let's answer one last question. So, what region in the electromagnetic spectrum can this photon be found? So, let's start first with letter A. So, the wavelength of a photon is 5.848 times 10 raised to negative 4 cm. So, convert the cm to meters, so that later when we involve the speed of light, whose unit is meters per second, we wouldn't have an issue. So, convert this into this. So, coming from scientific notation to, well, just fixing the decimal place and dividing it by 100, that value would be this, and you transfer that here. Since the formula is frequency is equal to constant over lambda, which is the wavelength. So that's speed of light divided by the wavelength, which is now in meters. You get the final answer, which again is either in over seconds or hertz. Either unit would be okay. Letter B. So what is the energy associated with the photon? This is the kind of question that demonstrates the importance of being familiar with well, that's actually for letter C, the one I'm trying to say. So if you're being asked to what region in the electromagnetic spectrum the photon can be found, you need to be familiar with these guys. So yeah, more on that later. Once we answer letter C, let's go to letter B first. Okay, so what is the energy associated with the photon? So there's something called, well, there's this formula called energy is equal to the Planck's constant times the frequency. Or you can say energy is equal to Planck's constant times C over V, because frequency again, C over, what is it? Lambda. I believe it's lambda. Yeah, so C over lambda. We're assuming, okay, that V is equal to F. Either letter represents the same thing, which is frequency. So the Planck's constant is always going to be 6.626 times 10 raised to negative 34 joules. And our frequency, well, we already computed for the frequency, which is which is the answer in letter A. So frequency, which is 5.13 times 10 raised to 13 hertz, you multiply that with the Planck's constant, you get the answer. You get the energy value. So, in answering letter C, what region in the electromagnetic spectrum can this photon be found? Not sure why the answer is separated. Perhaps I don't have an answer to that yet, but let's assess. What region in the electromagnetic spectrum can this photon be found? So you're not supposed to look at the energy. That's what I initially thought. You have to look at the frequency because again, in the region close to gamma ray, that's where you find the highest frequencies. If I recall correctly, I think that's 10 raised to negative 12 for gamma ray, 10 raised to negative 10 for X-ray, 10 raised to negative 8 for ultraviolet or UV, 10 raised to negative 6 for visible light. But how is that going to be helpful though? Because right now what we're looking at is 10 raised to 13. I believe this is where this illustration becomes useful. I take back what I said earlier, that you don't have to know this. I think you have to. So essentially what you saw earlier was a 1.3 times 10 raised to 13. I think that's what I saw. So essentially the 10 raised to 13, it's close to this. So what region does this correspond to? So microwave and infrared, but more on microwave. So the answer is going to be microwave. Yeah, even though the range here is usually just between 10 raised to 8 to 10 raised to 12, it can still vary. Because even for infrared, infrared 10 raised to 13 is within this range. So yeah. Okay, that's for this in this video. Next one will be on energy of radiation. Yeah, that kind of sort. Sunscreen, kinds of radiation, stratosphere, ozone layer, stuff, that kind of stuff. Okay, thanks for watching.